the same thing, the relations between U, H, A, and G are for open or closed systems. So working with H equals U, oops, sorry, I had it again. Normally you write this here, that's, shouldn't underline the open systems. Total, here is underlined with a D. So using U equals H equals U plus PV, I will get DH equals the dPV becomes PdV plus VdP. The PdV cancels that, so I get TdS plus VdP. And the GdN, G molar dN, is for all open system equations. So those parts change depending on which energy state variable I have, but there's always going to be Gibbs free energy times dN. And of course, if I'm doing it with mass, it would be hat times dN. dA, we can get it from either U minus ST. Well, no, we can get from U minus ST. So dA is du minus d of st, which will give me a minus tds minus sdt. The first canceling this. So I'm just talking them over because I believe we did derive this. And as you can guess, this is 6266. And similarly, using A equals U minus TS, we get dA equals minus S dt minus P dV plus G dN. Notice this equation can immediately be integrated if we define states with S and V. This can be immediately integrated if we define states with S and P. Normally you don't define states with S and something. This one gets immediately integrated if we define T and V. So that's an equation that often is going to be directly used. But what's the most common thing we normally define? Temperature and pressure. So the variable that leads to differentials of temperature and pressure is G, which is, one way to get it is A plus PV, and the differential of PV becomes PdV canceling this, plus VdP, so VdP replaces the minus PdV. Oh, oops, that's supposed to be 7. 8. Wait a minute, what am I doing? 7b, 8b. Here we go. 5, 6, 7, 8, and 5, 6, 7. Similarly, dg is minus s dt plus v dp plus g dn 6, 2, 8, 8. If we look at those relationships, any variable can be expressed as a function of the other two. So I can express u as a function of S and V, right? If I express u as a function of S and V, that means that the differential of u is going to be the partial of u with respect to S ds plus the partial of u with respect to V dv. Oh, you have the camera there? You have to do something else with the camera. I think it's blocking you. I really want to move it. I think it's blocking you.
Oh, you can move it.
Okay. So if you want to arrange it, I'll try to do it. I think here it doesn't block anyone, right? You can adjust it if you want to.
Okay.
So du, that make it not look like this, would be partial u with respect to s at constant what? The other variable v ds plus partial u with respect to v at constant what? S dv. Okay? Here I'm saying I have u as a function of s and v. Having u as a function of s and v means that I can write this expression for du. Comparing now this with 625b, we immediately get that I must have temperature equals to partial u respect to s. And I must have minus pressure equal to partial u respect to v. Clear, everyone? So, let's see, do I have any equation numbers for this? No. Comparing with, that starts for with, 625b means the temperature must equal partial u with respect to s at constant v, and minus pressure must equal partial u with respect to v at constant s. Okay? This has partial with respect to s at constant v. This has partial with respect to v at constant s. I can take a second partial. From here follows that I write the right-hand side first, that partial with respect to v at constant s of partial of u with respect to s at constant v is equal the partial with respect to v at constant s of t. Okay. On this side, I can take the partial with respect to s, excuse me, the partial with respect to s at constant v. So I get partial with respect to s at constant v, or I can put it directly of what I have here, of minus p at constant v. Equals partial with respect to s at constant v of partial u with respect to v at constant s. These are smooth functions, and for smooth functions and everything, where everything is well behaved, no infinity, is nothing like that, the order of the partials in a mixed second partial doesn't matter. So this part is equal to this part. Okay. It's the same thing. This is first partial with respect to v, then partial with respect to s of u, first with respect to s, then with v. It's simply changing the order of the segment of this mixed partial. Okay? So that means if the right-hand sides of the two are equal, the left-hand side must be equal. And of course, partial of minus p, I can put the minus outside. So we just derived the first Maxwell relationship. So inequality of those two that the partial of temperature with respect to molar volume at constant s is equal to minus the partial of pressure with respect to entropy at constant volume. I don't think I have individual text equations for this, but I'll use M's to indicate Maxwell. So this is the first Maxwell relationship. There are 4 Maxwell relationships we can get. Notice what we did here. We took the first equation, and we observed from this that T must be partial of U with respect to S at constant V. And minus P must be equal partial U with respect to V at constant S. So we have for T and minus P partial expressions. And if we now take this partial on this and this partial on this, right-hand sides are the same, so the left-hand sides must be the same. Okay? I can do exactly the same thing with the remaining 3 equations I have here. Let's do it, but I'm not going to go in the same detail. So, if we look at 6.2, 6b, the coefficient here, temperature, is what? Is the partial of this, of H, with respect to S, at constant P. Okay? So I have T is partial H with respect to S at constant P. And I have that V equals partial H with respect to P at constant S. Which means that the partial of this with respect to P at constant S must equal the partial of this with respect to S at constant. So from here follows that partial of T with respect to P at constant S is equal partial of V with respect to S at constant. That's the second Maxwell relationship. 6 to C. 6 to 6C. No, it's not 70. 70. Okay, let me get some help. Let me see a hand raised.
For the third one?
Yeah, for the third one.
TA.
No, I want to see a hand. Okay, Brian, he rose the hand first. Okay, what do I write, Brian?
So we have S.
Okay, let's keep it, so make it obvious with what it has in front, so let's keep the minus.
Okay.
So I will get minus S is equal to what partial? So what is in front here is which partial?
Is it the, oh, DA? Oh, wait. Yeah.
Yeah, DA is good.
DA dt.
At
At,
constant?
constant P? No, constant V, that's right.
Better not be at, this is the T, better not be at constant T. Okay? Partial A with respect to the variable, keeping constant the other variable. All right, one. You can do the next one. What is the next expression I get from the same equation?
TA divided by
Now tell me what I write first. Equals.
negative P equals
Okay, negative P equals.
TA divided by PV at constant T.
Divided by what? dV? Oh,
Constant T.
how is that put it right? This should be constant P. This should have been constant TV. Ah, okay, for some reason 2P. Okay. At what constant?
T.
T. Clear, everyone? So, if I take now the partial of this with respect to V at constant T, and take the partial of this with respect to T at constant V, I will have equality. So that means the left-hand side partial we expect to be at t, so we get partial of minus s with respect to v at constant t is equal to partial of minus p with respect to t at constant v. And of course the minuses go out and cancel out, so you'll allow me to write, since the minuses cancel out, this result. And of course that's the third Maxwell relationship. Okay? Any questions? All right. Let me see a hand from the last 6 rows for the next one. Someone from, come on. So this is 6 to 8b. So this equation here. So what do I say about this equation? Negative s, very good. Equals partial. At constant. P. Okay? Someone who hasn't spoken from the first, okay?
V equals dg over dp constant t.
At constant?
T.
Excellent. And go ahead and tell me what is the result from this? Okay, I can have a hand. Christian.
D negative s with respect to dp.
And you allow me to take the negative out, so s with respect to p, keeping what constant?
T.
Is equal to
dv over dt.
excellent. Okay. So that's how we obtain the Maxwell relationships. Okay. So I guess I never wrote the name. Maxwell relations. Okay. So let's move towards practical regimes. And we're interested in making calculations with different fluids. And what do we have available typically? We'll have typically available, or many times available, a volumetric equation or state model, which means a relationship between molar volume, pressure, and temperature. The simplest one, of course, being ideal gas law. And we also have typically available to us a temperature dependence of Cp, at least in the ideal gas, and also we'll have a, okay, so we'll have a temperature dependence Cp, and that can give us expressions for H and S. So if I have a volumetric equation of expressions for H and S, I can immediately calculate everything else. Let me write it. So information usually available